Hello students, welcome back. So we have been studying the interference of light and we came to know that interference is the superposition of light, and we have studied interference by division of wavefront. So as I told you, interference by division of wavefront means that wavefront is getting divided. So we had certain examples: Young's double-slit experiment, Fresnel biprism, Lloyd's mirror. These things we have learned in interference by division of wavefront. And another thing that we have seen is a phase change on reflection. When light goes from a rarer medium to denser medium and it is reflected, so the reflected beam have additional path difference of lambda by 2 plus or the phase difference of pi. So this thing will make use in the subsequent lectures. So let us move ahead and talk about the another concept, interference by division of wavefront amplitude. Division of amplitude. So as you know, a wave is characterized by certain parameters. Let us say phi is a wave and equal to a sine omega t plus phi. So in this wave, a is the amplitude, omega is the angular frequency, t is the time period, phi is the phase difference basically. So this argument is phase, and light is from minus infinity to plus infinity, so we are not taking this into the consideration because light was ever there and will ever be there. So when we talk about interference by division of amplitude, what we have basically, for example, we have this surface, water is here in this container. So index, let us say index is N1 of air, N2 is of medium, and N2 is greater than N1. Light is going into a denser medium. So what is basically happening when you shine it? Let us say amplitude A is incident. So part of that will be transmitted A2, let us say, and part of that will be reflected A1, let us say. So it can be seen that amplitude A is getting divided into A1 plus A2, and also there will be reflection from this point. If it is N1 outside, N1 is air index, so at this point also there will be transmission, there will be reflection. So you can see that A2 is further divided into, let us say, A3 and A4. A3 plus A4. So the all thing that can be seen from this example, the basic thing that we are trying to look is the amplitude is getting divided. So when these divided amplitudes will meet together and superpose with each other, will result into a interference pattern, and that is called interference by division of amplitude. So the simplest example you can take here is a soap bubble. Soap bubble, when you see, you must have done some experiment like bubbles, soap bubbles basically. छोटे बच्चे करते हैं ना, जो खिलौने रखते हैं बेसिकली, उसमें क्या होता है, एक सोप सॉल्यूशन होता है और ऐसे वो फूक मार के देखते हैं कि बबल्स बन रहे हैं, बबल्स जो हैं कलरफुल होते हैं. So that is basically a interference pattern which is in the category of by division of amplitudes. If this is clear, then let us talk about. So we have the case like this is index N1, this is index N2, and again it is N1. So when you shine light, there will be transmission, there will be reflection from this point, there will be reflection from this point, and transmission from this point. So if this is A, this is, let us say, A2, and this is, let us say, A1, and this is, let us say, A3, and this is, let us say, A4, and this is, let us say, A5. So you can see that when A1 and A5 will superpose, they will result into a interference pattern. It can be a maxima, it can be a minima, depending upon the path difference or the phase difference conditions. So basically, when if this medium is of thickness T and index, let us say, N2 or mu2, whatever you write, so the light which is traveling a thickness T in index N2, or in books we are written mu, so we can also take mu1 and mu2. You can also take mu1 and mu2. So the light reflected from the first surface, which is, let us say, A1, reflected from the second surface and transmitted again, let us say, A5. So the ray, first ray is A1, second ray is A5. So A5 ray has travelled additional path 2 times. This has gone and entered and reflected. So it has travelled 2 times. So we'll write 2 mu. If the index is mu2, and if we are not using index air as mu1, so we can drop this subscript basically. So 2 mu t. This is the path difference generated by light when it travels from an air medium to another medium, let us say, of index mu and thickness t. So this is the path difference will decide whether there will be a maxima or a minima. So the first reflection is from a rarer medium to denser medium, this surface. Second reflection is from a denser medium to rarer medium. So the first reflection will result into a path difference, additional path difference, which is equal to lambda by 2, and the second reflection will not result into an additional path difference. So this 2 mu t plus lambda by 2 is the total path difference. Lambda by 2 is coming because of the reflection from the first interface. This is air, this is water, let us say. So this first interface is, so this is because of the light travelling in the medium index mu thickness t, and this is because of the reflection from the first surface. We have taken lambda by 2 only from the first surface. This is the first interface. There is no reflection path difference, additional path difference because of this interface, which is, let us say, A4 is passing. So we have total path difference between ray A1 and A5 equal to 2 mu t plus lambda by 2. If this equal to n lambda, there will be a maxima. If this equal to n plus half lambda, there will be a minima. So the right hand side will always be n lambda for maxima and n plus 1 by 2 lambda for minima. So the only thing which will change is the additional path difference because of reflection from a rarer medium to the denser medium. So the only thing which you have to take care is if there is any additional term, so this will go in that side and will change the condition. The basic condition will remain same. You have to take care only about if there is any additional path difference generated for light going from a rarer medium to the denser medium. So in simple manner, if you write 2 mu t plus lambda by 2 can be taken on right side, so it will become n minus half lambda. This is the condition for maxima. And for the minima, because half is on the left side, half is on the right side, when it goes, it cancels off and will give 2 mu t equal to n lambda. This is for the minima. There will be a dark spot when the path difference condition is this one, there will be a bright spot when the path difference condition is this much. So it is just a matter of the path difference. You can have bright, you can have dark, depending upon the condition that we are facing for a particular medium of index mu and thickness t. So n is integer here, it can be 0, 1, 2 and so on. So now let us move ahead and talk about another topic, that is oblique incidence. In a normal incidence case, you can see in various textbooks that, for example, light is, you are shining this surface, this is partially reflecting. So by partially reflecting means, if the ray is going like that, we have shined with light this surface, this is partially reflecting. So by partially reflecting, I mean the 50% coating is on back side of this glass plate. So what will happen? It will be reflected like that. And if we have another surface, let us say some medium or some mirror, so that will be again reflected. This is water, let us say. So first surface will be reflecting and transmission will be there. Second surface will further be reflecting. So these reflections from the first, reflections from the second will meet by passing through this transparent 50% transparent material, that will result into a maxima and a minima. So this is just a matter of path difference condition to get a maxima and or minima. Okay, so let us talk another case, and we have the interference by reflection conditions. So we have another case, that is oblique incidence. So this is medium or material of thickness T, let us say, and we are shining light at some angle, let us say this one, and of that there will be normal, and we have the reflection from the first surface and transmission into the second surface. We have another normal here, so there will also be a reflection, and from this point there will be a transmission. This will also pass through like that, and from this surface there will be a reflection and there will be a transmission. This is very simple case. We have a amplitude A and getting divided into these many branches, this and this and that. So these are all things that are basically getting divided. So we have angle of incidence, let us say I here, so the reflection will be same. Let us write I again here, and if I write this point as B, this point as, if I draw a normal, this one, so this is let us say B and this is let us say N, this is let us say C, and this is let us say M, and if it is the center point, let us mark it as O. So it can be seen that there are reflections. This is the first ray reflected from the first surface. This is index mu. This is index air outside. So the reflection from the first surface, this ray, reflection from this surface, and is going in this direction, this ray. So these two rays are going to meet and will result into the interference pattern. Likewise, we have another two rays. These are the transmitted components. This will again add up and will give the maxima and minima in the interference pattern. So we'll do a bit of mathematics here and we'll quantify what is the path difference, and accordingly we'll write the conditions for the maxima and the minima. So it can be seen that when light is traveling by reflecting from the first surface, point B to N, this ray B to N, in that time light has gone B to M, M to C. So the path difference is basically dn minus dn minus, so bn is basically in the air, and bm plus mc. So it is basically 2 times, so I can write 2 times bm into index mu and thickness t. Wait. I'll repeat this diagram if you are not found with that. We have incident ray. This is the normal surface to the surface. The reflected ray. This is the transmitted component. We have the normal to the surface. Again reflection, transmission. So this will again come from this medium to that medium, and if we have normal here and here. So these are the transmitted components, these are the reflected components. So the all that we have to quantify is the path difference. So light has traveled this much in the airspace. Light has traveled from point, let us say, B to C. So in that point of time, light has gone into this length into plus that length. So let us say B, C, D and E somewhere here, and this is 50% of that. Let us say O here. So this is the thickness T, index mu, refractive index mu. So we'll calculate the path difference conditions. So BC is the index in air minus BD plus DE. So I'll write BD only, and 2 times index mu and thickness T. So this is the path difference which we have to calculate. If this equal to n lambda, we will get maxima. If this equal to n plus half lambda, equal to minima. We'll also take care about the additional path difference when light is going from air to index mu, let us say water, greater than that of water, air. Okay, so BC is basically, we have to calculate BC, we have to calculate BD plus DE. So BD 2 times we have to calculate. So this is the angle of incidence I here. This is again I angle because reflection will be on the same angle. And if you draw on this side, you have I here. And because the ray is coming like that, so this is also I here. So I'll apply mathematics here. We'll make use of the trigonometric formula. So in this triangle, this is the 90-degree angle, this is I. So you can see that what can we apply here? BC. BC is basically base. Sorry, BC is not base. This is base. This is perpendicular. This is hypotenuse. We want to calculate this and that. So P and H is here. So P and H is in sign. So I'll write P and H. So BC equal to BC upon BE. BC upon BE. So BE I can write here. This is sine of I. Simple. And you can see that BE is basically 2 times of BO. This is exactly in the middle of that. So I can write 2 times BE sine I. So from this triangle, I want to calculate what is this BO. This is O here. BO is here. So I would like to know what is this BO, this length. What is this? So I'll again make use of trigonometry. I know this side is T thickness, and this is, let us say, R refraction angle. So because this is also R, this is angle of refraction between this ray and that ray, so this will also be R. So I'll write this is 90. So base divided by hypotenuse. No, will not make it with the base. This is base and this is perpendicular. Base and perpendicular. We know perpendicular, we can find base. So I'll make use of tangent here. So BO. Alright, so P is basically T here. So T divided by BO equal to tan of R. So I can write BO is equal to T divided by tan of R. Very simple. So I'll make use here in BC equal to 2 times BO is basically sin I divided by sin I times T divided by tan R. So I'll make use of this in the next page. BC equal to twice sin R divided by, in fact sin I is here, this is not R, this is I. So BC, we have BC here as 2 sin I T upon tan R. 2, we have eraser, 2 sin I divided by tan R into, we have additional terms here, T. So let us go to the next page. T is there. So another thing we know is refractive index, mu equal to sin I divided by sin R. So I can write sin I equal to sin of I equal to mu times sin of R. This is R here. So we have BC equal to 2 sin R times T divided by tan of R. I must check here. Oh, we have mistake here. So see, tan theta equal to perpendicular upon base. So the perpendicular is this is not base, this is base, and this is perpendicular. So the only thing that will change is this will go tan of R here and T will be here. So BO will change automatically and ultimately we'll have, and this basically, so this will modify 2 sin R T into tan R times mu. So this will become 2 mu T sin R and tan R. So this will become sin by cos. So sin R will be here, sin R square divided by cos R. So this has been modified. This is BC. So एक बार. So we have calculated BC, and another thing is that expression we have BD plus DE. So I'll calculate BD and I will take the 2 times of that. Okay, so we have, so in that expression we have to calculate BD. So in that triangle we have a base here and hypotenuse here. So what I'll make is here this divided by that, so BD divided by T. So hypotenuse, it will be like that. So I'll make use of sine here. Sine of R equal to perpendicular upon hypotenuse. Perpendicular is here. In this triangle, what is perpendicular? No, I can't make use of sine here. We have the story of base and hypotenuse. So base and hypotenuse are in this. So base divided by hypotenuse. Base is this much. This is base. Both angles are on this line. So base is basically T divided by hypotenuse, which is, let us say, H. For some time I'll write H here, and this is cos of R. So H becomes T upon cos R. So H becomes T upon cos R, and we have to calculate 2 times of that. So 2T upon cos R. So it will be simply 2T upon cos R. So this quantity is 2T upon cos R. So I'll make use of this T upon cos R in that expression. Let us go to the next page. So it will become 2 mu T cos upon cos R minus 2 mu T sin square R divided by cos of R. So ultimately these things can be written as 1 minus sin square. So all the terms are same. 1 minus sin square is cos of R. So this becomes 2 mu T cos R. This will be the path difference calculation in this case. So I will simply write in this expression as 2 mu T cos R. This is the path difference, and the reflection has taken from rarer medium to the denser medium in first step. In the second step, there is reflection from denser medium to the rarer medium. So there will be only one path, additional path difference, lambda by 2. So this equal to n lambda will give you maxima, and if this equal to n plus half lambda will give you minima. So for maxima it is 2 mu T cos R equal to n minus half lambda. This is for the maxima. And 2 mu T cos R, so lambda right hand side, if you write 2n plus 1 lambda, so it will become n lambda. So this is the condition for minima. You can see that on right hand side we have condition for n lambda equal to for the minima and n minus half lambda for the maxima. This has happened all because of this lambda by 2 term. So the same thing that we have to derive is by adding lambda by 2 and right hand side by half lambda. So if you make use of these, you can write it as 2 mu T cos R equal to n lambda. This is the condition for minimum.